Swayam Prabha. Digital India. Educated India.
Let me go back to our discussion on thermodynamics, and today what I am going to do is discuss thermodynamics of multi-component systems or the systems with variable composition. That's the thing. Multi-component system or system with variable systems with position. That means if you have a system in which you have not only the single component, there are a number of components. So that's and these systems are particularly important for mixing of several substances or in chemical reactions where you mix different reactants and to obtain products. So they are all multi-component systems. So we need to understand the thermodynamics of these multi-component systems. So coming back to the basic thermodynamic function, as you know, one of the most important thermodynamic function is the Gibbs free energy. So Gibbs free energy, we start from the Gibbs free energy, and that G equal the Gibbs free energy is G, and that is the function of temperature and pressure if it is only a single component system, but say it has N1 moles for the component 1, N2 moles for component 2, and so on. So the point that I need to mention this in I is the number of moles for ith component. So G is a function of all these things, all these components, and as usual the function of temperature and pressure. And we know how to handle a single component system when we have only the variation of temperature and pressure. So I can write that change in Gibbs free energy dG, that is equal to dG equal to V dP minus S dt, that we derived some time back. If you start from G, from the definition of G is equal to H plus H minus Ts, and if you incorporate the first law of thermodynamics, finally we land up into this quantity. Then we see that this is something that we all know, and then the change in free energy is also associated with other things, that if we vary these numbers, that del N, del G, del N1, dN1, then when we keep Tp, then N2, these all constant, plus similarly we have del G, del N2 with Tp constant, and N1, N3, and so on, and dN2 plus the change in other components. So this is the basic equation for the change in Gibbs free energy. And so if we take constant temperature and pressure, so at constant temperature and pressure, Tp equal to constant, which is most often the case, then dG Pt, that is constant pressure and temperature, that is basically you can all these terms can be summed up in this form, that is mu I dN I, where this del G del N1 is the change in free energy per unit mole of the component 1. So that is mu 1, and similarly this is for the mu 2 and so on. So these are basically the chemical potential. So mu I is the chemical potential for the ith component. Now with this we now illustrate a very simple case of some mole transfer in a system. So suppose this is a system, and the system essentially has two parts. There are two regions here and another region is here, and say this I call region A and this I call region B, and I transfer dN amount from A to B, dN moles from A to B, where for A region chemical potential is mu A, and for B region the chemical potential B. So the change in chemical potential, is minus mu A dN plus mu B dN, and that corresponds to your change in delta G, and that is essentially, if you take dN common, then it is mu B minus mu A, and for automatic, or we should call spontaneous transfer of dN moles from here to here, or spontaneous flow of mass from A region to B region, depends on the sign of delta G. So if delta G is negative, less than 0, if delta G is negative, then mu A must be greater than mu B. So this region must be of higher potential, higher chemical potential. This is lower chemical potential. So from higher chemical potential to lower chemical potential, component can be transferred. So the component can be transferred from high chemical potential region to a low chemical potential region. And this is this has to be a spontaneous process. So this is something about again the use of delta G in following the direction of a flow of mass. That's the point. So that's an interesting, important point for when we will consider the case of mixing. Now we consider the typical case of a mixture. So I try to find out the chemical potential of a component in a mixture. The next question is, if we have a mixture, then what is the chemical potential? Chemical potential of a component in a mixture. Let us try to find out what this thing is. So suppose to actually illustrate this point, let us consider a box. Let us consider this box, and it has two compartments. They are separated by a barrier which is made of palladium. So palladium is a substance which allows only hydrogen gas to pass through. It is very small thing that can pass through, and not the nitrogen or oxygen or the other species. So in this component, left hand side, I put hydrogen, pure hydrogen, and on this side I have H2 plus and N2. It is a mixture. So what happens, that hydrogen gas can only pass through. So hydrogen can only pass through the palladium diaphragm. So if it is so, and now since they are just gases, they are hydrogen gas and nitrogen gas. On this side I have a mixture, and they can hydrogen gas can pass from here to here or here to here, and after the equilibrium is reached, so after the equilibrium is reached, then we find that the pressure on this side, that is P of hydrogen in the left, is the same as the partial pressure, that is the partial pressure of hydrogen on the right. That means where P is the total pressure, that is composed of partial pressure of hydrogen plus partial pressure of nitrogen. So the pressure, there is a pressure balance, that also tells us an important thing for an equilibrium condition. For the equilibrium condition, another thing must be valid, that is mu of, that is chemical potential for the chemical potential for pure hydrogen must be equal to the chemical potential of hydrogen in the mixture. That has to be ensured because of the equilibrium condition, thermodynamic equilibrium. So if this is so, now we know this follows from the equilibrium condition. Then we know that chemical potential of any substance, that is any ith component, is equal to mu I 0 at a specific temperature plus RT ln T, that is the pressure for the ith component. This is for for any pure component system. So if I write it purely, if I just remove the i's, it is just this that we have already shown. For an ideal gas, this is mu equal to mu 0 for one component, this is RT, ln P of that gas. Now we see that when we have mu of H2, that is pure, that is equal to mu 0 H2 plus RT ln P of H2. That has to be true because this is the pressure for the hydrogen. Now in the mixture, we talk about partial pressures, that is pH, pH2 and PN2. So in the mixture, mu H2, in the mixture we have mu 0 H2 T plus RT ln P of H2. That has to be the same because of this condition. These two are same, so I can write it exactly in this way. So another way that I know that P of, that is partial pressure of any substance, say if I have a mixture, then partial pressure Pi, so in a mixture, Pi is the partial pressure equal to Xi into total pressure. So this is the mole fraction of ith component. This is the partial pressure of ith species. This is for mole fraction of ith species, and this is the total pressure for the mixture. So that is the thing that we know. So for that reason, what we can do here, it is mu H2 0 at T, that is the pressure. 0 is assigned as for the standard state. That means when a pressure is P is equal to 1, then mu, these two mu's are equal. So that identifies this as the standard 1 atmospheric pressure. So that 0 indicates that standard pressure. So that is equal to RT ln, so P H2 equal to X H2 into P, total pressure. So that means I have a P plus RT ln X2. So this quantity I can identify as some mu of H2, which is basically pure, and the rest is RT ln X2, or I should not write it X2, but XH2. That is just to signify this is the mole fraction of hydrogen. So mu H2, so mu H2 in a mixture, that is clearly the mu H2 when it is pure plus RT ln mole fraction of H2. So, this if I generalize for any ith component, so for any ith component, I can write mu I in a mixture is a mu I pure. So, I can write it as a pure, P means pure, plus RT ln Xi. This is basically the expression that we are trying to find out, is the chemical potential of a component in a mixture. Chemical potential of ith component in a mixture, that means the difference between the two, that is the pure component and the component in a mixture, they differ by this amount. And since this is Xi is the mole fraction, Xi is the mole fraction of the ith component. So, it is always less than 0. It is always a fraction, sorry, it is always a fraction. Since Xi is a positive fraction, then this term mu I is always less than mu I pure. That means the chemical potential of an ith component in a mixture is always less than the chemical potential of that pure compound, pure component. This is because ln x ultimately becomes a negative quantity, since it is less than, it is just a fraction. So, that means chemical potential, when you put a system, put a component or a species in a mixture, they try to, or in a gas, I am talking mainly about gas. So, the gases tends to mix up because of the fact that the chemical potential, the final chemical potential of the component in a mixture is always less than the chemical potential of the pure substance. So, that means this quantity is negative. So, mu I is less than this, and that makes this that's why the gases spontaneously so because of this thing, this is also true for liquid. So, that is if the chemical potential of the final thing in a mixture is less than the chemical potential of the pure substance, then they when you mix them, they simply mix up spontaneously. So, that is an important thing. Now, we just try to understand the process of mixing and its thermodynamics, and in some detail. So, let us move on to the process of mixing in some detail. So, mixing of several components. So, let us assume that we have 3 components at a temperature T p, same temperature pressure, same temperature, pressure, they remain constant, and this is component 1 and this is mu 1 P, this is pure, mu 2 P for the component 2 and mu P 3 for the component 3. So, initially I have a system in which there are three compartments and there are 3 gases and they are gaseous substance, and so this is my initial state. So, this is the state of 3 gases. So, this is a chemical potential for the component 1, this is a chemical potential of the component 2, chemical potential of the component 3, all in the pure state, and they are separated, they are kept separate under separate condition. Now, we mix up. After mixing, so that means I have my free energy for the initial state, say initial state, that is equal to sum of mu I Pi Ni. So, I say I have Ni number here, N2 number of particles here, N2 mole, N1 number of moles here, N2 number of moles and N3 number of moles. So, you have to sum over all these quantities are equal to 1, 2, 3. Now, after mixing, we get a final state for which the free energy is initial, now it is final. It has a similar structure I, that is mu I, not P, it is for the pure substance, it is the chemical potential of ith component in a mixture times Ni. So, this gives me, so delta G, the change in chemical potential, G final minus G initial, that is equal to, final is this one, so Ni times mu I minus mu I P. So, that is the chemical potential of the pure substance minus the chemical potential in a mixture. So, that is the very simple relation that we find out. Now, delta G equal to change of potential is Ni times mu I minus mu I P. So, what is this mu I? Now, I know what is this thing mu I. So, mu I minus mu I pure substance, that is equal to RT ln xi, that is the mole fraction of the ith component or ith species. So, this means I have delta G equal to I Ni RT ln xi, or I can write it in a slightly rearranged form, that I write, say Ni sum over Ni, say equal to N, N1, N2, N3. If I sum it up, I have total N number of moles. So, N is the number of moles. We multiply it and divide it by N. This is a sum over the all ith component. and that is RT ln xi. Now you see that Ni by N is the total number of moles divided, it is the number of moles of the ith component divided by the total number of moles, and that is equal to xi. So this is xi. So I have RT nRT I xi ln xi. So delta G is something that we can derive very easily. That is the free energy of mixing, and you can see that it is always negative because ln x is, since ln xi is less than 0, delta G is less than 0. So free energy change is negative. So the mixing occurs spontaneously. So that's a spontaneous process. The mixing of the gas is a spontaneous process that is easily seen. Now, within 1 or 2 minutes, I find out all the other thermodynamic quantities that are required. So, suppose we know that the G equal to H minus Ts, or delta G equal to delta H minus T delta S, and that gives me that delta G del of T partial derivative, that gives me equal to minus of delta S. So, if I differentiate this quantity with respect to T, I have a very simple form, and that is equal to delta S. Easily you find out it is minus, sign will be there, n r sum over xi ln xi. So only T is not there because this has been differentiated and it has been removed. So delta S is basically this quantity, and you see that there is a minus sign here. Since this is a negative quantity, so delta is always positive. So on mixing leads to increase in entropy. So entropy change is positive for mixing process. So now what is my delta H? Delta H can be easily found out by delta G plus T delta S. That's a very interesting quantity, and you see delta, what is my delta G? Delta G is basically nRT sum over xi ln xi I minus, if I multiply it with T, then T times delta S is minus nRT xi ln xi, and that is equal to just 0. So there is no change in thermal condition of the system. That means when the mixing is ideal, there is no change in the thermal component, or there is no heat generation. So no thermal effect is there in the mixing. So, and the process of mixing is therefore completely entropic, not So anything, since this is 0, so delta G change is entirely due to entropy. So the mixing is therefore a purely entropic effect. So this is something about the thermodynamics of mixing, and we stop here, and we will discuss other multi-component systems when we will go over to chemical equilibrium. This is just about mixing and an entropic effect and the thermodynamics of mixing. So thank you all for your attention.